Okay, so the next talk is finding complete impossible differential attacks on AND RX ciphers and efficient distinguisher for AND ARX design by the Basmita Chakraborty, Hossein Hadipur, Fong Hoa Nguyen, and Maria Ayusedo. The Basmita, please give the talk.
Thank you, Yosuke, for the nice introduction. And hello, everyone. I'm Debushmita Chakraborty, and today I'm going to present finding complete impossible differential attacks on AND-RX ciphers and efficient distinguishers for ARX design. And this is a joint work with Hossein Hadipur, Fong Hoa Nguyen, and Maria Ayusedo. Okay. So before starting this work, our motivation was to construct a efficient automated tool to find complete impossible differential attack for AND-RX and ARX ciphers, as there are lack of such efficient automated tools. And uh, then in this work we actually provided the efficient automated tool to find ID distinguishers for AND-RX ARX ciphers, and it actually improves the previous automated model for ID distinguishers in several directions. And therefore we extend the distinguisher modeling to a unified CP model to combine both the distinguisher and the key recovery thing to find a complete ID key recovery attack for AND-RX designs. And we applied this on the AND-RX ciphers Simon and Simek and got some improved result. So a glimpse into our results, we can see that for the 5 variants of Simon, we got 1 or 2 rounds of improvements. And for the rest of the variants, we didn't get round improvement, but we improved the complexities by a good margin. Okay, so now this is the plan of today's talk. So we are starting with the background knowledge and the previous works regarding impossible differential, and then I discuss about our method for searching distinguishers, and then how to extend this to find the complete ID attack, key recovery attack, how to extend it to find a unified CP model that I will discuss, and then I will conclude my talk for discussing some future works. Okay, so moving on to the first part about the uh, background part. So starting with a very basic thing, the most fundamental and popular cryptanalytic technique, classical differential cryptanalysis. The main goal is to recover the secret key by analyzing how the input difference propagated through the ciphers. And for the overview of the technique is like first choosing the input pairs of a fixed difference, say delta U, and then observe the output differences by encrypted plaintext pairs, and saw the difference at delta L, and try to find the input output differences with high probability and try to exploit these differential characteristics to deduce the full key. So that's a very brief overview. And then moving on to our main topic of our talk, that is impossible differential cryptanalysis, where we are trying to exploit the differentials of probability 0, that means that never occurs, to eliminate the incorrect key guess. So the steps of the impossible differential cryptanalysis, like first we have to find impossible differential, which can be found using a mid in the middle technique, and then build a key recovery attack on this. So diving deep into the algorithm. So first we are starting with a impossible differential, say delta U to delta L, input and output difference. That means they propagate with probability 0. And then just like other statistical attacks, we can extend this distinguisher part in both direction, from delta U to delta L, we can move backward and forward with probability 1 and get the truncated difference as delta B and delta F. And then the next step is to find the involved key bits, that's KB and KF, in which actually helps us to partially encrypt and decrypt from delta B to delta F to come into the the starting point of the distinguishers, that is delta U delta L. So for the key recovery attack, the first step is to generate n pairs satisfying delta B and delta F, and then the guess and filter parts, where we are guessing for each involved key uh, we are first guessing the key, and then we are partially encrypt and decrypt from the input and output pair. And if it, boils down to the impossible differential, say delta U, delta L, that means the whatever key we have guessed, that is undoubtedly wrong. So we discard that key, and our goal for this impossible differential is to discard as many as wrong key, and then the brute force the remaining key candidates. And here, along with discussing the algorithm, I include the complexity of these steps, and I'm not going deep into these complexity analysis steps, so just to have a glimpse onto what are the required parameters which we need for the analysis of the complexities. So for that reason, I built like this way. So the next thing is that how to find the impossible differential. That's the first step, and that can be found using the miss in the middle technique. So miss in the middle technique is something like, suppose we are starting with a given input and output difference, a delta U and delta L, and from the input difference we are going forward direction for some rounds, and from the output difference we are going backward directions for some round. And to ensure that that given input and output difference is a impossible differential, so we have to find a contradiction in the middle. So just like this example, so for the suppose this is a AES block cipher. So we are starting with this input and output difference, and we are going forward for one round, and we are for the output difference we are going backward for 2.5 rounds. And we can see that after in the middle, after one round and backward 2.5 round, we can see there is a contradiction in the first column, where for the forward in the by the forward direction it was showing that the first column is have zero difference, and for the backward direction it is showing there's the first column is the non-zero difference. So it is important to note here. So sorry, it is important to note that, so by this technique we can find that given an input and output difference, whether this is impossible or not we can find out, but the main goal is to come up with an algorithm which can find appropriate input and output difference that is actually an impossible differential. So obvious way to find is by hand, but obviously that is not recommended because it is error prone and it cannot be handled for the large and complicated crypto systems. So we come to the automated solvers, something like that. We are converting the finding the impossible differential, the problem of finding the impossible differential, we are converted that problem into a constraint programming problem, and then like MILP or SAS, SMT or CP, and this constraint programming problem we are just giving into the solvers, the constraint solvers. Okay, maybe MILP solvers, Gurobi, or maybe CP solvers, and then from that we are having that we are constructing the ID distinguishers. So obviously it is quite clear the importance of automated tools, that it automates the exploration of the vast search spaces, and it improves accuracy because it actually reduces the probability of human errors, and also it's capable of handling the large and complex crypto systems, and also it speeds up the cryptanalysis procedure and ensures the repeatability and uniformities testing. These are the importance of automated tools which are quite clear. And now so these are the main motivations of finding the automated tools for ID attacks. So come to the previous works related to this. So these are some previous works which works on the automated tools for ID attacks, and most of the tools mainly focused on formulating the automated tools on ID distinguishers, and sometimes they need to fix the input and output differences. So for this reason, this kind of solvers cannot be extended, cannot be used to construct a unified model to find the whole ID key recovery attack. And sometimes fixing the input output differences can lead to checking for all possible cases. So now, recently, there is two works on Eurocrypt 2023 and USD 2024 by Hadipur et al. So they have actually proposed a satisfiability-based CP model to find ID distinguishers, and they then, based upon this, they have extended that model to construct the unified model to find ID key recovery. Mostly they, applied this to the word-oriented ciphers also, but in TOSC 2024, they have extended it to bit slice ciphers. They have applied it to, I guess, present and ASCONs, but they restrict, in that case, they restrict themselves to only ID distinguishers. So here comes to our application. So we are focusing on the ARX and ARX ciphers. So these are the ciphers where we are focusing on kind of block ciphers for ARX, Lia, Spec, Chacha, CPAS, Stesky, and for ANDRX we are focusing on Simon, Simek. So these are the one round functions regarding related to the ARX ciphers, whatever I have mentioned, and these are the ANDRX round functions of ANDRX ciphers, and So moving on to the next part of our talk, that is searching method for searching distinguishers. So before moving on to our method, I think I should explain a little bit about the model, the previous model on which we have constructed our model. So for this, suppose we are trying to find the IT distinguishers of R round. So for that, we, split the block cipher ED into two parts, the upper part of RM rounds, say, and the lower part EL of RD and RM rounds. And then we are trying to model the forward propagation of truncated trails with probability 1, say, we are just denoting this model, and the next model of the backward propagations with truncated tails of probability 1, and try to find the a model to ensure the contradiction at the middle round. So this is proposed by the Hadipur et al. At Eurocrypt 2023, and in TOSC 2024 they propose, there they advance the model a little bit, where they relax the limit of fixing the contradiction locations. For this, this is quite obvious that they model the forward propagation in the similar way, they model the backward propagation, and then they model the to ensure the contradiction at any one of the intermediate round, like this way. So, and now as we are working on ANDRX, ARX ciphers, so we move on to the bitwise CP model to search distinguishers. So already in TOSC 2024, Hadipur et al., the authors already use their bitwise CP models to truncate the, to encode the truncated differential trails, and for their bit representation, differences at each bit positions, they encoded via an integer variable like 0, 1, and -1, like fixed difference 0, one is fixed difference once, and -1 in unknown difference. And for propagation rules, as they have applied in the present and ASCON, so they actually model the propagations for ZOR, branching, and S boxes. But as we are working on the ARX and ARX ciphers, we need to model the and modulo modular addition operation. So this is a propagation rules for modulo addition operation. So just like this, we are expressing the modulo addition operation as a composition of n-1 full adders and a half adder G, where G is simply ZOR operation, and there's a CP variables I am denoting, and then the CP constraint corresponding to the truncated differential transition with probability 1 through the modulo addition. It will be the n-1 full adder, and the ZOR operation with the constraint C n-1 is equal to 0. So regarding the full adder, the operation is from the definition of modulo addition, that f of xyc is the ZOR of xyc, and the majority function of xyc, and this is the constraint related to the truncated differential transitions with probability 1 through the full adder. And now, till now, we have everything to model ARX to find ID distinguishers for ARX and ARX ciphers. But here we made one more addition, that whatever we have discussed till now, it's regarding the, the forward. So we move the input difference forward, we move the output difference backward, and try to find the contradiction in the middle. But this is something kind of direct contradiction. But there may be some kind of complicated contradictions may happen that may not be detectable by the direct checks. So in 2018 by Sadeghi et al.'s paper, they have first give this kind of concept of indirect contradiction, but the authors in their paper, do this kind of find this kind of indirect contradiction by the manual approach. So in this work, first time we have automate this concept into our model, and now I'm going to explain how we are doing this. So the first of all, the forward propagation through EU, as we can see in the blue color. This is the forward propagation and the backward propagation in green color. And then suppose there are no direct contradiction in the middle. So we are merging the information what we got from the forward and backwards. If suppose is XURM and XLRM, we are merged the information and suppose got the new information as MXRM. And then we are propagate this merged information in the both side, forward and backward, and try to find contradiction with the original forward and backward. That means merged backward, we are trying to find contradiction with the original forward, and the merged forward, we are trying to find a contradiction with the original backward. So this is the kind of model we have constructed. And yeah, so this is a advanced model to identify indirect contradictions. Now we have make the a little bit of advancement that we construct one model that can find any one of the contradiction, either that may be direct or indirect. So something like that, we got the model for forward and backward propagation, just like the previous I have discussed, and merge information in the middle. And now we propagate the merged information in the both side. And now we are trying to check any one of the contradiction. It can be with the original forward and backward, that is direct contradiction, and whatever I have explained, the merged backward with the original forward, and the merged forward with the original backward. So this is a kind of, we have incorporated the idea of indirect contradiction into our automated model. So yeah, so the advantage of our distinguisher modeling is quite clear, that extends the, we have extended the prior works to find distinguishers on ARX and ARX ciphers. And our model is obviously based on the satisfiability of the CP model, which eliminates the need for the fixing the input-output difference. And obviously, we incorporate the idea of indirect contradictions into our model, other than the previous works. And obviously, we find the longest existing distinguishers and numerous new trails revisiting the old ones applied on the ARX and ARX ciphers. And for ARX ciphers, we have actually extended to a unified model for key recovery. So this is our glimpse into our results of ARX ciphers. One can see that we have proposed, I mean, we have showed some new results on some ARX ciphers. And also we have found some new trails in which we didn't got the improved round improvement in the distinguishers. And for the indirect ciphers for Simon Simek, we didn't have any round improvements in the distinguishers, obviously, but we got some new trails along with revisiting the old trails. And this is some examples of Chesky, where you can see the, for the two rounds of, I mean, two round forward and two round backward, we got the contradiction. And for the spec, I think it's 96, we got the two round forward and four round backward, we got the contradiction. So now moving on to our complete CP model for ID attacks. So for this thing, I think that we first model the distinguishers, okay, whatever I have explained. And then for the upper and lower part, we model the filters in the EB and EF, and that is CBCF, and then model the guess and determine part. In this method, we actually model the involved subkey bits, and then finally we model the equivalent subkey technique. That technique is something which I try to actually reduce the number of involved subkeys, and then we model the essential parameters, I mean related to complexity formulas, and then minimize the total time complexity. This is the complete overview of the CP model. I'm not going into much deeper into the equivalent subkey technique, but this is something which actually helps to reduce the number of guess subkey bits by replacing the original subkey bits. Like this, we move the ki of round I to I minus I plus 1, and ki of round I. For the backward part, it is move ki of round I to round I minus 1, and for upper part, it's move ki of round I to I plus 1. And this is the mathematical formulation, like the relationship between the original subkeys and the original subkeys and the equivalent subkey. This is the relationship of for the forward and backward part. And this is the corresponding figure of Simon, where you can see for the first A and B figure, the K0 in moved, I mean, lower to K1E and K1 to K2E. And similarly for the backward part. So the efficiency of our unified key recovery model, it's obviously, it's all the large versions of Simon, and also we have this kind of results in within few hours in a regular laptop. So that's actually depicts the efficiency of our tool. And this is a simple examples where for Simon 64128 we have one round of improvement from the previous works. This is a kind of figure, and this is the results. Yeah, so whatever for CIMEC, yeah, it's a so the conclusion, I'm really sorry. So yeah, I'm moving on to the conclusion part. So whatever I've discussed, this much of enhancement we have done. And for the future works, I think developing a CP model for complete idea attacks for ARX designs, that's left as a open problem, and extending CP models via ARX and ARX designs, and optimizing key recovery techniques, maybe using CP models. That's an interesting future works. And okay, these are the references. Thank you so much for your kind attention, and I'm happy to hear questions.
Okay, so thank you very much for the talk. So if you have a quick question, so you want. Okay, so nothing. Okay, so thanks a lot. So the next talk.
Thank you.